Almost every program you use picks one of two transport protocols. TCP when it wants reliability, UDP when it wants speed. Yet a third one has existed for over 20 years, quietly carrying the world's phone calls. It is called SCTP, the Stream Control Transmission Protocol. From your program's point of view, it looks familiar. You open a connection to a peer, you send, you receive. The inside is where it diverges sharply. Its connection setup takes 4 messages instead of 3, and the extra step exists for one reason: a signed cookie that lets the server refuse to remember anything until the client has proven it is real. It does not hand your data over as a shapeless stream of bytes. It preserves message boundaries, so the thing you sent as one unit arrives at the other side as exactly that same one unit. Inside a single connection, it carries many independent streams. That one design choice removes the single most annoying weakness of TCP, the way one lost packet freezes absolutely everything behind it. And a single connection can be bound to 2 different IP addresses at each end at once. If one network path dies mid-conversation, the connection itself simply keeps going over the other one. With features like that, you would expect it everywhere. Instead, you have almost certainly never used it directly, and the reason is a piece of hardware sitting in your home and in every corporate firewall. So let us walk one connection all the way through: the cookie handshake, the message boundaries, the parallel streams, the second address, and finally the middle box that pushed all of this off the public internet. Step 1. Your application asks for an SCTP connection, which the specification calls an association. You give it a destination and it starts a handshake that looks, at first glance, a lot like the TCP one you already know. But there are 4 messages, not 3. You send an init. The server replies with an init carrying a state cookie, a small blob holding everything needed to build the connection, signed with a secret only that server knows. Here is the trick. The server allocates nothing yet. It keeps no half-open entry. You must echo the cookie back, and only when the signature checks out does the server spend a single byte of memory on you. That makes the classic SYN flood pointless. An attacker firing a million fake connection attempts fills no table because there is no table to fill. The defense is baked into the handshake rather than bolted on afterwards. Now the connection is up and you send data. TCP would treat your bytes as one endless stream and let them merge, leaving your code to hunt for where each message starts and stops. SCTP does not do that. SCTP is message-oriented, like UDP. Send a 400-byte record, and the receiver is handed exactly 400 bytes as one unit. No length prefixes, no delimiter parsing, no half-arrived record sitting in your buffer. Next, that single association is split into streams. You might open 16 of them, 1 per phone call, 1 per subsystem, 1 per chat room. They share the same connection, the same congestion control, the same handshake. Now lose a packet. In TCP, everything already delivered behind that gap sits in the kernel buffer, unreadable, waiting for one retransmission. That is head-of-line blocking, and it stalls data that arrived perfectly fine. With streams, only the stream that lost the message waits. Streams 4 through 16 keep delivering to your app at full speed. One missing chunk on one call no longer freezes 15 other conversations. Then there is multi-homing. Each endpoint can register 2 IP addresses when the association starts, say 1 per network card. One becomes the primary path, the other sits ready, both belonging to the same single connection. The stack sends quiet heartbeat chunks down the idle path to check it still works. Unplug the primary cable and traffic moves to the spare address within seconds, without tearing the connection down or telling the application. So why is none of this in your browser? Because the packet leaving your machine carries protocol number 132. Your home router and your firewall were built to rewrite only numbers 6 and 17. Anything else is unknown, so it gets silently dropped. A protocol that cannot cross a home NAT cannot win the public internet, no matter how good its design is. It lost on deployment, not on merit. It is not gone, though. Mobile carriers run it between their own core network boxes, where there is no consumer NAT in the way. Call setup signaling between operators has ridden on SCTP for 2 decades. And you use it every day without knowing. Every web RTC data channel and every video call app is SCTP, wrapped inside UDP so the middle boxes see something they recognize and wave it through. It can also relax reliability per message. A stream can be told to give up retransmitting after a deadline, so stale data is dropped rather than delivered late. That is how a data channel offers both reliable and unreliable modes. Its ideas outlived it. Modern protocols carry independent streams over one connection to dodge head-of-line blocking and migrate a live connection between addresses. SCTP got there first, on the wrong layer. So the full shape: a cookie handshake that refuses to hold state, messages that keep their borders, many streams so one loss stalls one lane, and 2 addresses so a dead path never kills the connection. Hidden machinery shown. SCTP is the protocol that solved problems we are still solving today and lost anyway because the boxes in between had never heard of it. Follow how it all runs for more. See you next time.